while the other guys talk.
And we are live. Hi, ast111x. And we're here for our second YouTube hangout, office hours for 10,000. And my name is Frank, and I'm the instructor for the course. And what do I like to do? In astronomy, anyway. In astronomy, I like to sort of blow things up. Things that go boom in the night sky and all the things that happen from that. So you get the fireworks from that, you get the 4th of July fireworks going from that, and all the elements that it makes out of that. So it sort of makes the periodic table and all the ramifications of that for galaxies and solar systems, which is the topic of this course. And also with us today is Bill Wolf and Tom Marsden, and I'll let them introduce themselves.
Hi, I'm Bill Wolf. I'm a postdoctoral researcher also at ASU. I work with Frank, and I'm also interested in the ways stars die and explode. So I look at how binary stars in particular with white dwarf stars, which are these interesting stars that are roughly the size of the Earth but the mass of the sun, and what happens when you dump fresh fuel on them, and they explode in ways known as novae, and also a particular type of supernovae.
And I'm Tom Marsden. I used to work at Intel, but now I went to grad school and I just finished up my PhD in astrophysics. I study the early, yeah, woohoo, graduation in 2 weeks. Yeah, I studied the early universe when the first stars formed and ionized the then neutral hydrogen. And today the universe consists mainly of ionized hydrogen. So sometime in the past, it went from neutral to ionized via the galaxies, stars, black holes that formed at the time. So trying to study that with an antenna in Western Australia, where it's nice and RFI friendly.
Hey, I got a question. Since you're doing first stuff in the universe, what's your estimate on when the first solar system formed in the universe?
Oh, first solar system.
Yeah.
Oh, wow.
Is that detectable with your antenna array?
Oh, no, definitely not. It's just one antenna looking at the average sky signal, pretty much the delta on the CMB that the neutral hydrogen can cause through absorption of the 21 centimeter line.
We're studying this week, 21 centimeters. People should pay attention to that.
Yeah, that's important.
What we do this week on 21 centimeters, what part of what Tom studies. But I'm curious though, really, what somebody must have looked at this, right? When was the first solar system in the universe formed, or about? Take your choice: time, redshift, amount of heavy elements in the universe, right? There must be some minimum you need to form a solar system. Although it may not look anything like our solar system. I don't know.
I would think they came along with at least the second population of stars.
Or later. What an interesting question.
Yeah, what is that? 100 million years, 150 million years after the Big Bang?
Something like that, when the first ones go off.
Yeah. It has a wide range of estimates as to when the first stars formed. So. Right.
Huh. Okay. Well, I have an interesting question to answer myself. What was the first solar system? What did it look like? Maybe it all only had hydrogen planets, right? Maybe they're all gas giants or something.
Could be.
Okay. Speaking of questions, we have a few questions lined up that people have asked, and if you're listening and we have a number of viewers here, go ahead and post your questions, and we'll try and pick them up as we go. So let's just go ahead and through the questions. We got one here from Jessica McMillan. And Tom, I think you're going to take that one, so go ahead.
Well, do you want me to take that one with the full presentation?
Sure, go for it.
All right, great. A timely question. I have to share my desktop. Okay, can everybody see that?
Yes.
All right, great. So something exciting happened last month. We had our first confirmed visitor from outside our solar system. I'll talk about why we know that it didn't belong to our solar system, and a little description as to maybe a few more details as to what this thing was. So as we know, we have our normal location for asteroids. We've got our Trojans, our Greeks, and so on. And they're sort of orbiting around between the orbits of Mars and Jupiter. So what we had was a visitor that came in almost perpendicular to the plane of our solar system, had a close encounter with our sun, and got deflected on out. Early on, it was thought it was a comet, except the search for the dust tail and gas tail came up empty. So a week later, they concluded it was an asteroid and not a comet. And since it was discovered by an astronomer in Hawaii, they gave it a Hawaiian name. I think it's pronounced something like Umau. I'll give you my pronunciation guide later on. In Hawaiian, it means the messenger from afar arriving first. So this was a pretty exciting event. So some details about this. It was first seen on October 19th at the University of Hawaii by postdoc researchers. So 3 cheers for postdocs. Rob Warwick. And that was 5 days after the closest approach to Earth. So thank goodness it wasn't on a direct path to the Earth. Not sure we would have noticed it too far in advance. Anyway, his colleague Marco Micheli also saw the object using a ESA telescope in the Canary Islands. And there wasn't too much data, so they needed to collect some more to figure out what the path of this thing was. And as you might guess, it became a pretty hot topic, and observers and astronomers from all over the world were looking at this thing and figuring out, taking more data so they could figure out its speed and trajectory. So they concluded that it was going 50,000 miles per hour before entering our solar system. And then with a gravity boost, it sped up to 98,000 miles per hour upon exit, which is too fast for the sun to contain. So they decided this thing couldn't have been something that the sun could own and capture. And the orbit was hyperbolic, meaning it's not a closed orbit and it's not going to come back. And it's still in our solar system, but it is so dim and so small that it was only visible for about 2 weeks from the time we first noticed it to the time it went away. Like I said earlier, it was originally thought to be a comet, but there's no gas or dust tail. So a week later, they figured, okay, this is not a comet. And through the speed, okay, it's not one of our asteroids that went astray and got some sort of gravity boost from Jupiter or something. It was given the Hawaiian name of Umau, and by November 3rd, that was 2 weeks later, it was too far away and faint to be seen. We observed it for 2 weeks and then had to say goodbye. So again, there's the path of it. That's pretty cool. I believe it came within 0.2 AUs of Earth, which is not too close, but not too far. But one other really unique thing is that it had a really odd shape. It was cylindrical and light pink. I believe that's similar to the color of asteroids in our solar system. But it it was at least 600 feet by 100 by 100. Some people say similar to a fire extinguisher or a cigar or a raw sausage. And they're not completely sure just how long it was. It might have even been 1,000 feet by 100 by 100 roughly. So it might have even had a 10-to-1 aspect ratio. So that was really cool. Like how could you get something so cylindrical like that? Usually through collisions and other things, they turn out to be round. So that's pretty cool. Here's a list of some sources that have the articles on it, and I also have a couple of fun links. Here's one of them. This was just today. A little bit about the asteroid that tumbled past from another system. Ratio 6-to-1, 10-to-1. That's pretty good. Some speculation, some other objects. Monolith, Star Destroyer, huge eggplant emoji. Blah blah blah. But so that made XKCD today. So that's kind of cool. And one other interesting link, if I can find it again. Okay, and here's a 10-second pronunciation guide. Okay, that's enough of that. Okay, yeah, since that song got stuck in my head after looking at the after noticing the similarities to it, I thought I'd share it so you could get that song stuck in your head as well. So
I didn't hear it, Tom.
Oh, you didn't hear it?
No. Probably something about sharing audio or something.
Yeah,
that
screen
could be.
sharing probably doesn't share the audio.
Okay, so yeah, click on the thing will be posted later, and so definitely click on it or do a Google search for Papa Mau Mau, and you can get the song stuck in your head too. All right.
Awesome. Feeling Hawaiian here for my Thanksgiving. So I did do a quick little search, and the oldest planet that has so far discovered, the oldest star that has planets around it is some telephone number, which is not terribly important, but it's about 12 billion years old. It has carbon and oxygen and iron that's only about 1% of what the sun has. So it has 100th of the heavy metals that the sun does, and it has 2 gas giants around it. So apparently the planetary process can work even at 12 billion years. Let's say it's go on the lower end, that's 12 billion. So that's still, 1.5 billion after the Big Bang. So at least the process can get going at that point. Whether there's older ones or not, I don't know. But it's interesting, we can already find planets around fairly what are called metal poor stars, just meaning they have a lot less heavy elements than the sun. So what's the minimum metallicity for life? That's another question. Okay, what else do we got in the questions? We've got sort of a question on whether we should advise Elon Musk to pull the plug on Mars and go to Titan. I don't know Elon personally, so I don't know. Certainly an option. And then we've got another one about magnetic fields. You want to take a shot at that one, Bill?
Sure. So the question says from Jen Grace, my question is about magnetic fields and how we have learned they deflect solar radiation away from a planet, along with the many atmospheric layers we have on Earth. Is there technology in development or already in use that would utilize this fact to protect our astronauts during the space flight? So yes, what Jen's talking about here is the magnetic field of Earth that actually protects our atmosphere and us. not necessarily from solar radiation, although it's sort of related. Though the sun is constantly emitting the stream of charged particles at a very high velocity. I actually don't remember how fast it is, but it's extremely fast, that just goes throughout the solar system along the ecliptic. And those can actually damage the atmosphere. It can ionize things. It could harm us. It can harm satellites. But the magnetic field, the way that magnetic fields work is they actually channel particles. So if a particle flies into a magnetic field, it actually gets sort of trapped going around this spiral path following the magnetic field. So it prevents the solar wind from doing a whole lot of damage to things here on Earth. And then it creates these things called the Van Allen belts, where all these charged particles are sort of trapped, and then as it's spiraling through, it actually gives off radiation of its own. So these belts of radiation are actually a little bit dangerous on their own. You can find plenty of conspiracy theories of why people don't think NASA could have ever worked, and that there aren't people didn't walk on the moon because the Van Allen belts would have killed them. It's nonsense, but there is a kernel of truth that these Van Allen belts do contain some radiation. And so then the idea here would be that there would be some sort of technology utilizing something similar. You create a protective magnetic field in your spaceship that could protect astronauts from the solar wind. I personally do not know of any sort of developed technology for this. This seems like a detail that if we want to travel through the skies, Earth, to other planets, we would need to account for this. I don't know if you could just design a spaceship hull that's strong enough that you don't need to worry about these particles, but I actually haven't done the math on that. So I've not heard of this technology. I don't know if Frank or Tom, if you have heard anything like this, but to my knowledge, I don't know of anything like that.
Yeah, I haven't heard anything about deflecting. What I do know, because in a previous life, I used to work at a silicon chip foundry in Silicon Valley, and one of the things I did was design and test these particular types of devices for space applications. So when you make these things, the term that is used is you make them radiation hardened. So you make them rad hard. And so you make these things, and I would say in general, the solution is you just make things thicker to be able to withstand the radiation and charged particles that Bill talked about. So you don't try and block it as much as you just try and have it not affect the device that you're working on. So they tend to be bigger, fatter, thicker. But they are
put a big coat on the stuff.
You put a big coat, and then you envelope your instrument package in lead or things along those lines to help mitigate the problem. But yeah, there's a whole all those satellites that are up around in high Earth orbit. All these things have radiation hardened technologies in them to protect their delicate electronics as they go.
But yes, so it doesn't sound like there's many ways where people put in, some powerful magnetic field source in something to, instead of hardening it, just deflecting stuff around. So it seems like
that's to my knowledge. I think that's sort of like a terraforming question, sort of. I could be wrong, but it seems like that would take a lot more.
This is the concern with Mars, isn't it? That it doesn't have a magnetic field, or it has a very weak magnetic field, so you'd want to find a way to shield it.
Mm-hmm. Right. Yeah, that goes back to the other question of, well, why don't we do Titan? Because presumably the solar wind would be less out there.
Yeah, personally, I'd like to see us train on the moon first.
Yeah.
A little bit closer in case you have an emergency.
Yeah, what was that movie? The Martian?
Yeah.
Had some emergency, you had to go do something. And then, of course, we had real life stuff, but we didn't send out the cavalry to go save them, so to speak.
Just whip up a moon mission in a couple of days.
Yeah, I do know there are some active proposals out there to put telescopes on the moon or in a lunar orbit to help protect them with this. I know there's one gamma ray mission that is being discussed. That's far different than being funded and far different than actually flying. So it's kind of a concept of putting a telescope that will catch high energy photons, gamma ray photons, from things that like what Tom studies on black holes, colliding neutron stars, and other highly energetic processes. And there's some definite advantages to having it orbit on the dark side of the moon. So, speaking of, hey, for all of you Mercury lovers out there, or if you've never seen Mercury and you want to see Mercury, tomorrow, what is it? Today's the 22nd. Yeah, so tomorrow, Mercury, which orbits close to the sun, happens to be at its farthest distance away from the sun. It's called the greatest elongation on the evening of tomorrow. So if you want to try and take a look at Mercury, your first shot or your repeated shot, tomorrow is a great time to do it because it's the farthest away from the sun. And so once the sun sets, you will be able to get your best shot of it and longest shot of it that you'll get. If you do see it, Mercury will be in the waning gibbous phase, given the angle of the sun, Mercury, and Earth. So tomorrow's Thanksgiving and Mercury Day. Yay! Okay, I wanted to do a little chat on time. We covered time a little bit in the very beginning of this course, and I thought it would be a good time just to wrap up some stuff on the topic of time. So I'm going to share my screen share. I'll just do my whole desktop.
Hey, Frank, just a comment on Mercury. People should be able to see Saturn right above it.
Yeah, Saturn and Mercury will be as close as they're going to get.
Yeah, it's
a couple of days.
It's kind of hard to see Mercury because the sky is so bright when you're looking at it. But if you line up Saturn and sort of follow that to the direction of where the sun set, it's a little bit to the left of it.
Right. Cool. Can you see my screen okay?
Yes.
Yes.
Okay. I shall just launch. The passions of astronomy are no less profound because they are not noisy. That's from John Steinbeck, The Short Reign of Pippin IV, who is a story about an amateur astronomer. So this is sort of the only comedy that Steinbeck ever wrote. But he's an amateur astronomer, and through a twist of fate, he happens to be elected the King of France, which he decidedly does not like because it takes him away from his astronomy, and so he will often dress, as the book cover shows here, as a commoner, and then heads out into the countryside to continue his hobby of astronomy. Eventually, he's thrown out as King of France over the period of a month or two, and it's sort of a commentary on politics as well. But it's a great story about an amateur astronomer, so check it out. I want to talk a little bit about time through the ages. Here's a star clock, and we're going to be talking about clocks a fair amount and where they come from and why they are the way they are today. Okay, it's when humanity is getting going and we're starting to learn how to do plants and do agricultural dependence on your society. That means knowing when to plant, when to pick, when the first frost comes, and so your clock is set by the seasons. That's all fine. But as societies grow up and they get older and they get more complex, they want to have fixed dates for things like my birthday or your birthday or the 4th of July, like on the image on the right, on the 4th of July in Tempe, Arizona, or Thanksgiving, as the case may be. Pay your taxes. All these things, societies want fixed dates on when you're going to do things. And this immediately introduces the fundamental difficulty, which we're going to talk about over the next 20 slides or so, of keeping the seasonal calendars, that is the time as the sun says, and the calendar years, which is the time humans want, synchronized. You have to keep them the same. Otherwise, you might end up with Christmas in during the hottest part of the year or something like that. So we have this fundamental problem of wanting to fix dates and then keeping that synchronized with the sun. So just for reference, as we go along, the seasonal year is defined as vernal equinox to vernal equinox, and it is about, roughly, 365 days, 5 hours, 48 minutes, 46 seconds, or about 365.25. We'll round that off, okay? So 365.25 is a number to kind of keep in your head here, and we'll revisit that number here as we go along, because that's important for keeping the clocks synchronized and the persistence of time there from the melting clocks of Dali. Okay, so when humanity is getting rolling, the yearly calendars were often based on things like summer solstice to summer solstice, or when a particular star first rises with the sun, and this is known as a heliacal rising. The image here is showing the heliacal rising of the star, one of the brightest stars in the northern hemisphere, Sirius. So there's the sun on the left, there's Canis Major, which is the dog constellation, and within that is Sirius. And so to mark time, the Egyptians used Sirius, and when it rose in early July in Egypt, and this was when the Nile was in flood. And with an economy based on the floods, agricultural dependence and all, the heliacal rising of Sirius was the most important, and hence the very first day of the year. So they didn't use January 1, they used sometime in July. Here from there, I'm at 2000 BC here, and so this is happening on July 15th, 2000 BC, and you're seeing the rising of Sirius with the sun, which would then mark the opening of the year in the Egyptian calendar. So this is still with us today. There's Canis Major, the constellation there, and it's because it's in the constellation Canis Major, it's referred to as the dog star. And it's from the Egyptians' use of the heliacal rising of Sirius in early July to mark the beginning of the year, is where we get the phrase dog days of summer. Because that's when the dog star is rising. So even that turn of phrase is quite old, and it's still with us. Like a lot of things with astronomy, once it gets ingrained, it hangs with us for quite some time. So that was kind of a year. How about a month? A year is kind of a long time, and people wanted finer granulations of time. And so the first thing you might think is to use the moon. And in fact, the moon is the root word of month. So when we just talk month, we immediately are pulling up the moon within that. And there's a shot of the Aztec calendar stone. That's a lunar-based calendar. And so they use the moon to mark time. But there's two main problems with using the moon to subdivide a year. The first obstacle is that the lunar month varies a little bit. If you're going to go from full moon to full moon, let's say, it sort of varies between 29 and 30 days. And this variance is due to using something called the synodic period, which we're going to talk about, rather than the sidereal period. Sidereal period. So a synodic period is what it looks like, right? Full moon to full moon. And it relies on the same alignments between the sun and the earth and the objects you're looking at. It's easily observable. It's not so useful. The one you really want is the sidereal period, and I always remember it as sidereal, so it's the real period, is the time between identical distant star, earth, and object alignments. This is the real period because this is the period you would stick in something like Kepler's third law, Newton's variation of Kepler's third law. So it's the real deal, but it's also a lot harder to observe. And I will just walk through sort of the difference between those as we go. So here we have the sun, we have the earth, we have the moon going around the earth, and then we have a distant star. And I'm going to start my clock when everything happens to be aligned. So the sun, the earth, the moon, and the star are all aligned in my time equals 0 starting point. Okay, so it's a full moon right? Because the moon is on the backside of the Earth there. And I've also got an alignment between the moon, the Earth, and my distant star. So now you're going to let time go by. Okay? And so now, when the Earth and the moon and the distant star line up again, okay, when they go on that straight line as the Earth orbits around, this is the real period. This is the sidereal period, and it's 27.322 days for the moon. But the moon is not a full moon, right? Just in the image, the moon, because the Earth has moved along its orbit, the moon has to go a little bit farther. Okay, so it takes a little bit of extra time to get back to the full moon phase. And so that is the synodic period, the observed visual appearance of the moon, full moon to full moon. Okay, and so that period varies around a little bit because the Earth's orbit is not a perfect circle, as we know well now. It's elliptical. And so sometimes it travels a little faster when it's closer to the sun, slower when it's farther away. And so the time to reach full moon varies. It's about 29.5, but it varies around a little bit. Okay. So that's one problem with using the moon as a marker, is that the most obvious thing you see, the phases of the moon, vary around a little bit. And the second one is that the average lunar month, 29.5, does not divide into 12 evenly. So 12 lunar months is about 11 days too short. 13 lunar months is about 19 days too long. And so if you strictly use the moon as the real clock, it will slowly get out of step with the seasons, so that eventually you're going to end up with the hottest days of the year during the winter months and so on. So many cultures, such as the Aztecs that we saw earlier, they got around this problem by inserting an extra 13th month every few years. And so this is how they synchronized the seasonal calendar, the time that the sun says, versus the calendar year, the desired fixed time calendar that man imposes on the order of the sun going through. So this is still with us, this lunar-based calendar. So it's kind of accepted practice 4,000 years ago that for about a month, 1 month after a wedding, the bride's father would supply his son-in-law with all the mead he could drink. And mead is a beer. It's a honey beer. You can actually still buy it. They make it out in places like in Oregon. You can get that in other places. And since their calendar was lunar-based, this period, this 1 month period after the marriage, was referred to as the honey month, or what we call today as the honeymoon. So, you know, traditions that are 4,000 years old and based on lunar calendars are still with us today in our terminology and what we call things. There's lots of other terminologies for the moon. We have things like the lunatic, that's where the word lunatic comes from, luna, la luna, lunatic. We have blue moons, wet moons, harvest moons. I just learned today we have something called the old moon I didn't even know about. So lots of terms based on the moon, but I like honeymoon the best, where that comes from. So the Egyptians, after a while, gave up on using the moon to mark time within a year, and they took a more radical approach. They are the ones that divided the year into 12 months of 30 days each for a total of 360 days. Now, they knew this was not close, and so at the end of every year, they added 5 days for an approximation to the year of 365 days. 12 was where does 12 come from? 12 was their base counting system. 12 was a revered number, let's say, a holy number to them. And that's the origin of why we have 12 hours of daylight, AM, 12 hours of nighttime, PM. It's why we have 12 months in the year, etc. So blame the Egyptians for why we have 12 months. And so they added extra days to keep their calendars synchronized. This repeating theme of keeping clocks and the sun synchronized. So this went on for a while until the Romans came around. And the Romans, for all their conquest and advances, had originally a very surprisingly messy calendar. Their year was 10 months long, and the first of the year was taken to be in March, the Ides of March, as the first month of the year. And extra days were inserted at random at different locations within the Roman Empire in order to keep the seasonal and calendar years together. The image there is a shot of what the Roman calendar looked like back when it had 10 months, and when to insert the various days. This calendar is still with us today. Okay, the very names that we use for the months, September, October, November, December, these are from being the 7th, 8th, and 9th, and 10th months in the Roman calendar. So if you speak Spanish or you speak any other Romanic language like that, you can just count to 10, and you will immediately recognize 7, 8, 9, 10 in there. Although they are no longer the 7th, 8th, 9th, and 10th months in the calendar, right? December is the 12th month, but we still keep the terminology from the Romans. So it's kind of weird to have month number 10 actually being month number 12 in our modern calendar, but still with us. So this was completely unacceptable for an empire the size of the Romans. And so 1 year before his untimely death in the Ides of March, Julius Caesar instituted a new calendar. So he picked up from the Babylonians. We're still going to have 12 almost equal months. We're still the Romans, so we're still going to have March being the first month of the year, totaling 365 days. So he hasn't done anything relative to the Babylonians. But now he takes the radical step and goes every 4th year, or a leap year, 1 extra day was added to the end of the year. And so over a 4-year time period, this gives an average year of 365.25 days, which is close to what the real average year is. Okay, and he not only implements this Julian calendar, but he implements it across the entire Roman Empire. No longer was town A allowed to have a different calendar than town B across the Roman Empire. Everybody had to have the same calendar, the Julian calendar. Now, Julian liked his calendar so much that he decided to take a name, one of the 12 months, for himself, and this is where we get July. So July is named after Julius Caesar in his new calendar. Money and power go together, kind of. And so Julius had some wealthy benefactors who are known as the Juno family. They powered the money side of the house, and he honored them by giving them the name of a month in this new system, and that's where we get the term June. So June is from an old, rich Roman family. And of course, now the pattern was set, and so every emperor after Julius had to take the name of a month for himself. That gets a little unwieldy. Only one of them actually stuck, and that was Julius's grandson, Augustus Caesar. And this is where we get August from. And so August for Augustus Caesar. And so the whole middle there, June, July, August, is all remnants of the Roman Empire and their institution of the Julian calendar. So the Julian calendar is pretty good. It's about 11 minutes too long in the year. That's good enough when your clocks aren't that accurate. Or about 1 day in 130 years, or about 1 week after 1,000 years. 1 week, you will notice that. And in fact, that's exactly what happened. Time marched on. 1,000 years went by. And all of a sudden, people started noticing that the seasonal calendar and the calendar that they were imposing on the sun didn't line up. And so this got to be such a problem that by 1582, they were about 10 days out of whack. And so Pope Gregory implements because now the Catholic Church is the de facto world power, introduces what is called the Gregorian calendar after Pope Gregory. And I want you to take a close look at this calendar from October of 1582. October 1, 2, 3, 4, 15. Oh my gosh. So tremendous amount of social unrest when this occurs. What happened to my birthday? My birthday is October 6th. I don't get a birthday anymore. What about taxes? Do I have to pay? Do I have to pay my employees for time they didn't work between the 4 and the 15? So lots of unrest when you just kind of arbitrarily chop off 10 days out of the calendar. But that is what happened. And people got over it. They figured out all the social details of that. And it is with Pope Gregory that we then introduce the next refinement to the calendar year. This is the Roman Church, so we can't have that Roman March as the first of the year. And so it is with Pope Gregory that January 1 then becomes the beginning of the year. That's the origin of that from 1582. Every 4 years, an extra day is to be added in February. So he basically picks up the Julian calendar. At this point, he hasn't really done anything. It's the same. He's just shifted the origin point from March to January. But now he implements a new rule in that century years that are divisible by 400 are also leap years. And so century years like 1700, 1800, 1900, these are not leap years because they're not evenly divisible by 400. But the year 1600, because 16 divided by 4 is 4, 2000, 20 divided by 4 is 5, are leap years. So 2000 was the last time we had a leap year. And you also add an extra day during those century years. So this is sort of like the next refinement to the calendar. And so this system is only about 38 seconds too short relative to the seasonal calendar, or about 1 day in 2,200 years. So by this time, we've kind of learned our lesson. What are we going to do? Are we going to wait another 2,200 years until the calendars are out of sync by a day and go through the whole rigmarole again? No, we've learned our lesson. And so now in the modern era, 1 second is added to the calendar clock either on June 30th or December 31st, whenever the difference between the seasonal year and the calendar year get out of sync by a second. So it's variable. It moves around a little bit because the Earth is wobbling, the Earth is spinning. There's lots of influences that can affect things. The Earth is slowing down because from the moon. So there's lots of things that can affect the timing up until about 1 second. And so we do that synchronization twice a year, and perhaps you've read that in the paper also. No, there's an extra second at midnight on the 31st. This is why, because we're keeping the seasonal and calendar years synchronized. So the calendar clock is the time we want, and that is maintained from a worldwide network of atomic clocks where we decide what the time is. And then the seasonal clock, what the sun says, which ultimately is the one we really tie to, is based on the Earth's rotation. And that is set by this hunkered down bomb shelter looking building there on the bottom. That's from the, it's provided by the Earth International Rotation Service. That's actually out at the Naval Research Laboratory. That's where they keep track of that. So that's kind of the story on how we got to where we got on our year. There's lots of historical baggage in our terminology going through the Babylonians, through the Romans. And as we covered a little bit, how come, if you want to subdivide the year even farther, how come there's 7 days in the week? How come there's not 5 days in the week? How come there's not 10 days in the week? Where did 7 come from? Well, the 7 came from because to the Babylonians and beyond, there were only 7 objects that changed their position on the night sky, and that made them very special. And so we call these the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn, and each one of them has their special day to it. And so our names come from the conquerors of Rome. And so we have Sunday, Moon Day, Tuesday for Mars, Woon Day, Mercury, Thor Day, Thursday for Thor. Freya, the only female in the whole group, is Venus Day, and then Saturn Day. And so we have 7 days of the week because there were 7 things that moved on the night sky. If you want to subdivide even farther, where did time zones come from? Where'd that ever get into the game? Why do we do this? So before time zones, everybody used to properly set their time by the local condition of the sun. That's just the most natural thing to do. But this created tremendous problems once we started to have organized transportation system, in particular the trains. So if a train is supposed to, leave New York at 5 and it's supposed to get to Austin, Texas at 7, whose 5 or 7 is that? Is that local time? Is that the time in New York? And it was just tremendous amount of confusion when everybody uses their own local times to set that. And so time zones were actually introduced in the United States in about 1883 to standardize schedules so that people knew 5 o'clock Eastern, 10 o'clock Mountain Standard Time here in Arizona. And so by 1918, it was the U.S. Congress made the rail zones the official time zones of the United States. And that was followed up a few years later, and I think in about the 1927s or so, by the forerunner of what is now called the United Nations, and I forget what the name is off the top of my head, and they implemented the worldwide time zones. So time zones come from our desire to have a fixed schedule for our transportation systems. And that is what I wanted to say about time. So thanks.
That's pretty interesting, Frank. Before the telegraph and the trains, people probably didn't care what time it was anywhere else.
Yeah, who cares? Yeah. If you can't get there, right? If it's beyond your causality, causality sphere, who cares?
Yeah.
Does not affect you.
Frank, is there a non-cultural reason why we wouldn't just obey the edX way of things and just use UTC for everyone? Just to sound like whatever noon is now known as 5 a.m. because that's where we are in the world, and then we can just be done with all this.
Yeah, that's true. That's true. I think people would have a real hard time with calling when the sun is at its highest point in the sky 5 a.m. somewhere.
Yeah, you just need one generation.
It's probably, that's the social part, right? That's like Gregory cutting 10 days out of the year, right? Complete social chaos. And so I think if people did that, everybody had the same clock, based on UTC, people would rebel. And the other thing is, you'll notice that originally the time zone lines were geodesics. They were straight, so to speak.
Yeah, that would make sense.
And unfortunately, that doesn't work due to local geopolitical.
Well, I saw all of China's one time zone, which is crazy. Yeah. But they went with my approach of just there's one time, I don't care what time the sun rises and falls, deal with it.
There you go. And so the time zones they look zigzaggy based on local geopolitical rationales.
Yeah, if you split a city in half with a time zone, then that's bad.
Well, then you've got funny things like, not to beat up on them, just saying, you have places like Indiana in the United States where different locales can decide whether they're in the Eastern time zone or the Central time zone. And so you can go from one town to another, and all of a sudden you'll jump an hour because one decides they're in Eastern and one decides they're in Central. So it's sort of this quilt patchwork of time zones in Indiana. And every couple of years they have some, they're going to try and straighten it out. We're going to be Eastern or we're going to be Central, and it doesn't really go anywhere. So they still have their idiosyncrasies. And of course, here in Arizona, we don't do daylight savings time. And that comes up every couple of years, this whole daylight savings time shift thing. Why do we do this? Why do we still do this? May have had a rationale in the past, but why do we do it now?
And the Navajos,
it doesn't go anywhere.
And the Navajos opt out of it too. So
I'm gonna vote for Bill as time czar. He gets to set the time everywhere in the whole world.
Work starts 4 to 5 hours after sunrise. So get used to your new regime by Czar Bill.
Yeah, look how smoothly the transition to metric went in the U.S.
Oh yeah, that one.
Right. You can't have a democracy. You need to have a dictator set these things.
You have my vote, Bill.
I actually had another question for you, Frank. So you had mentioned that the Gregorian calendar is about, on average, you lose about 38 seconds a year, or gain. I can't remember which direction it goes. But then you said sometimes we'll add an individual second to fix this. And I don't get how 1 second every now and then compensates for 38 seconds.
Oh, because it's not uniform. Sometimes there is, sometimes there isn't.
Okay. But it seems like you would need to add things in chunks of more than 1 second to do anything to compensate for a 38-second lack every year.
I think fair point. I don't know the answer.
But also, I mean, like the fact that you're changing when midnight happens seems like that shouldn't work. I mean, that seems like that's more related to the slowdown of the Earth. I think I've heard it used as a metaphor of trying to count the number of times a ballerina spins on the back of a truck compared to how long it takes the truck to complete its journey. Like the two things just, the rotation of the Earth and the revolution of the Earth just do not need to be related in any meaningful way. So it seems like you would only add things in entire day increments to fix this sync up.
You're the time czar.
Okay, well, I'll come up with something and get back to you.
No, but you ask a fair question, right? So the question is to make, if you're adding 1 second twice a year at max, how does that square with the average time that the Gregorian calendar misses? That's a fair question. I don't know that, but I'll look at it. Maybe I'll post something on the discussion boards. Speaking of, did anybody post any new questions?
I looked, I didn't see anything a little bit ago.
Okay. Okay. We have about 8 minutes or so. Let's see what we got. Anything anybody want to talk about? Okay, that works for me. You're the time czar, so you call.
That's true, yeah. I'll call
it. Can I make 52 minutes equal to an hour, czar?
I'll allow it just this once.
Oh, you will allow it. We're good. Okay. In that case, I think we're done. To those in the U.S., enjoy your holiday weekend coming up here as Thanksgiving rolls around. This is the last week for this course. We're in exoplanets. We're learning a little bit about 21 centimeter stuff that Tom does. Next week is the final exam. We won't be taking any questions about questions on the final exam, but we'll still be on the boards for a little bit if you have any residual questions. Otherwise, we're probably going to sign off sometime in the middle of next week. So the final exam is much like quiz number 2, proctored, for those who are taking it for credit. So it's the same level of difficulty, roughly the same number of questions, and so on. Okay, and with that, if you have any questions, please ask on our discussion boards. And with that, I think we will sign off for this run of ast111x, second one. Thanks, everyone. Bye-bye.
Bye-bye.
Bye-bye.